Multivariate regression. I have so many students coming to me feeling lost, confused. They get model output, they don't know how to interpret, they don't know what's in, what's out, and they start banging their head against the wall, just don't know what to do and feel unconfident. I'm gonna help you, and I've got for you an exciting live session where I explain multivariate regression so simple that even a 5-year-old can understand it. We're not dumbing it down, but what we're gonna do is make this simple and accessible so that you have clarity going forward. And what I find as a professor is so often students have big gaps in their training. They just weren't taught well. I fundamentally disagree with a lot of the way stats is taught, leading with numbers and math. And for the vast majority of you who I work with, you're very intuitive and visual. And I'm gonna help you see and understand how regression is working so that you can apply it better immediately. What that means is we're going to have to take a few steps back before we go forward. But trust me, it's worth it. I'm Professor David Stuckler, and I had a lot of difficulty with stats along the way, along with other areas, academic writing, publishing, writing research proposals, and that's exactly why I created the Community Fast Track Grad, so that you don't have to go through all that headache and frustration that I did when I was sitting exactly where you are. So this is a fun live session, and it's the kind of live session that's gonna give you a sneak peek of what is 100% free and available to you in my Facebook group. Let me know what you think in the comments below. And with that, we are gonna dive straight in, starting from first principles. And by the end, you're gonna have so much more clarity and you'll wish that you had found this sooner. So often what I find, and I think kind of as a background, I'm gonna pull up a whiteboard because I just find a lot of the students who I work with are very visual, and especially with quantitative stuff, I don't like the way quantitative stuff is taught because it's taught often based on math. And you guys aren't mathematicians. Most of you don't want to be mathematicians. So it's not that helpful. Well, one distinction that I often raise in the world of statistics is, because many of you are learning this for the first time, is we have this kind of bright line between, right, understanding what the research question is, what you want to do, what this is all about, and then figuring out, well, how am I going to go then put that into practice? And I think the thing that's easier for most of you is to wrestle with these questions, these what questions. And this is like, what's the gap in my research? What is my research question? And what is going to be then the right kind of design that can answer my research question? And for many of you, that does lead you to a quantitative design, but I want you to have real clarity, because sometimes I do talk to students and they've got the gap, which is great. From that gap follows a nice research question to fill that gap, right? And from that research question, then you have a plurality of different designs. And sometimes I do find some students struggling because quantitative methods aren't the right design for the question. But I'm going to assume, for the purpose of the discussion today, that quantitative methods are right for your discussion and for your research. Yep. So if I'm going to assume they've already decided that quantitative analysis is right. But then when you get into design, right, there's a whole swath of tools and techniques that can be bewildering. And so people then immediately start jumping over. They then cross this bridge and go into the world of how. And it's like, oh, well, logistic regression or multivariate or instrumental variables or difference in difference. And you can really get lost. So the research is already complex. I want you to think of things very, very simply and come back to first principles. So the core in quantitative research, right? I'm going to draw some more space. The core thing that you're doing in quantitative research is you are looking at a relationship between two things. You are really it's really quite blunt. It's like, because it's based on an idea of correlation, and correlation is pretty much how things relate together. So if one thing goes up, does the other thing go up with it? That's a positive correlation. If one thing goes up, does the other thing go down? They're negatively related. If one goes up and the other one just kind of stays the same, well, then there's no relationship. And that's kind of really, quantitative tools are much more blunt in that way, right, than qualitative tools, because you're really looking at really what the nature of a relationship is between two things. Let me make, I think it's helpful to give a clear, concrete example. So let's say, there's one study published in the New England Journal of Medicine that said, okay, in countries where people eat more chocolate, do they have more Nobel Prize winners? Okay, and right, what did they look at? And they showed a graph that said, hey, hang on a second, here's the different countries. And here, we've got more chocolate being eaten in countries. Each dot here was a country. And here you had, right, how much chocolate was being eaten here. And over here they had the number of, oops, and I'm on a different keyboard, so I can't figure out where the hashtag is. Oh, shoot, I want the number. There we go, number. Nobel Prize winners. And they found this. And so you guys can see, just like I spoke about a moment ago, that there's this positive, seemingly positive relationship between the two things, right? And we call that a positive correlation or positive association or a correlation, which is called positive correlation to keep that simple. Okay. And that's it. A lot of your research, in most of your research, right, if you are moving into a world of quantitative stuff, you should be able to think already right now, what is my main relationship that I'm looking at? What am I trying to show? What two things am I trying to connect with data? You have at least two. Many of you may have multiple things, but at the most very basic start, you need to have two things. And often these things are called, right? It's important to get the direction right. This is sometimes called the exposure, and this is called the outcome. Some different fields have different ways of talking about this. This can be called, in economics, they like to call this the independent variable and the dependent variable. And the dependent variable, why? Because this variable, they're trying to say, depends on, we think the amount of Nobel Prize winners depends on how much chocolate you eat. Okay, now, I don't actually think chocolate creates more Nobel Prize winners, but we're using this as an example for reasons I'm going to come back to. Okay, so all of you need to understand this direction and already have an idea, all right? And this comes back to your research question and the design you're going to set up. What is causing what? In this case, the way we've set up, we think the chocolate, eating more chocolate, we think somehow makes you more intelligent and is going to drive more Nobel Prize winners in a country. Okay, so I hope that makes sense. So it's very important. Right? Here's another tip. You need to have, so tip here, you need to identify and understand for yourself which variables are causing what effects. I hope that all makes sense. So you need to know that is to say, you need to know what is your exposure variable and what is your outcome at a bare minimum. Now, if you say, okay, my design, I want to test the relationship between chocolate and Nobel Prize winners, right? Well, now I have different design decisions. I could look at chocolate and Nobel Prize winners, right? You could look at it at different levels. So some research, right? There are two components to the research you've got to think about. One, you've got to think about is what level of analysis in quantitative work, and the other is how, if you're going to look at it, how you're going to look at it over time. These are two important dimensions of the data that you're going to think about in your design. So these are two dimensions that you need to be able to define in your quantitative analysis early on. When I say level of analysis, well, level of analysis is often, are you going to be looking at zooming in and looking at individuals? Are you going to be looking out at higher units like a city or a country or the world or something else? So that's what I mean by the level of analysis. Right? What is the right? And again, we're in a hypothetical world and we're still in the design. And so I want you guys to think about what is the right level of analysis for your research question. And you'll hear me talk a lot about design because I think it's really, really important, because so often I see people crossing this bridge, they go into the how, and then they get done with the how, but there's problems with their what. And so then they run back to this what, and then they have to fix the holes that they have there, and then they have to do the how again, and then here. And you see what happens here? That is textbook running in circles, and it's frustrating, and you just start to hate your life, and then you start to think you can't do it, you get burnt out, and then some of you come to me and are like, help, save me, and I'm like, you've got 2 weeks left in your program. The sad reality is it's too late. I worked in public health, so I always believe that cliche of ounce of prevention, I'm writing it because
love public health stuff. Ounce of prevention is better than a pound of cure. And that cliche is really true. Just move this somewhere out of sight, out of mind. Okay, so I want you to get the design right. So that level of analysis is really critical, if that makes sense. And in this case, our Nobel Prize winner examples, we are looking at the population level, right? Because Nobel Prize winners is kind of at how many does an entire country have. So that's going to be at the population level. So that's going to constrain our analysis and say, okay, we're going to look at the population level. If we instead were looking at, we set up a study to say, look at chocolate and intelligence. Well, here we could look at individuals, right? We could say, okay, let's take a group of individuals and see, okay, that positive negative correlation we talked about, if you eat more correlation, do you have higher IQ or some measure of intelligence? Okay. Does that make sense? But in this case, with the example we've gone through, we're going at the population level. Then you need to look if is it over time. Are you going to track and say, okay, when countries start eating more chocolate, do they somehow do the number of Nobel Prize winners rise? I don't think it makes a lot of sense, because it's not like there's an immediate you started eating chocolate and then there'd be a Nobel Prize winner. So you need to decide if it's going to be over time. In this case, it's not over time, And if it's over time, this is what Abel was talking about before. It's sometimes called panel or longitudinal, just longitudinal panel in the sense that we're following and tracking over time what happens. If it's just at one point in time, we sometimes call this a cross section, because it's kind of like taking a snapshot of one point in time. I think of it as chopping. It's like cross section. So in this case, this was a cross section stuff. Point is, these are some critical decisions that you need to make about your study, and this all comes back to your design. So I want you to think about what the right design is for your research question. Okay, so you've got kind of the two core dimensions of your design. How you're going to look at it. Now we need to get a little bit more into the substance. So let me talk a little bit about what I mean here. So effectively, I mentioned before, we've got these correlations that we want to look at. Now, in an ideal world, what could we do? We could say, okay, everybody in Kenya eats 10 pounds of chocolate a year, and everybody in South Africa eats no chocolate. And let's see if, as a result of that, Kenya gets more Nobel Prize winners. I hope you can see that this idea of a randomized controlled trial is completely senseless and is not going to work. But if we did that in a simple world, right, we would be a randomized controlled trial, what that would do, it would make everything basically everything about these countries would be pretty much then, with regard to chocolate, well, they would be pretty much the same except the chocolate. And so this is the idea of a randomized trial. The randomized trial is basically saying we're going to make everything the same, except for one thing. And that one thing you want to test. And so why am I teaching about randomized trials? You guys aren't going to go do a randomized trial. I mean, this is what doctors do. They want to know what blood pressure medicine works, so they need to make sure everything's the same, so we know we can kind of forensically go in and pinpoint this one drug we are testing is responsible for the effect we're seeing, because everything else is the same. And the magic for doing that is randomization, because through randomization, we make everything the same. Okay? Yeah, I hope that makes sense. But we don't live in a world of randomization. We live in a world, most of you, of where there's non-randomized or observational. We're taking data that we've observed or somebody else has observed, and we're going to try to do the same causality. And this is where it's so important to draw up a DAG model, what I call a DAG. So coming to our first principle. So in non-randomized, right, if we had randomly put people to chocolate or not chocolate, we could pinpoint the link between chocolate and its effects. A DAG is called an acyclic graph. It's just kind of a logic model that sets out the causal logic that you want to study. Notice we're still in the world over here. We're still in the world of design. We haven't gotten to the how yet. Why? Why spend so much time on design? Because we need that design before we start putting into practice. It's the same thing when I talk about writing. You need to know what you want to write before you start writing. You need to have that clarity, or you're going to set yourself up for frustration. Okay, so these DAGs are critical in setting out your logic. So what we had before, chocolate. Okay, we had chocolate and Nobel Prizes, and we think there's a link there. But we can go deeper. We need to deal with things on this chart that might affect the relationship we want to study. So one thing here is another thing that could drive Nobel Prizes is better income or better education. These things can all drive, right? A richer country is likely to have more Nobel Prizes. A more educated country is better to have Nobel Prizes. You guys could probably think of a lot of things that are going on here. Now, if you look at this immediately, you can also see we got an issue. This income is not only linked to Nobel Prizes, but it's also linked to chocolate. So stands to reason where there's more income, there's also more chocolate being consumed. Where there's more education, maybe there's more chocolate being consumed. I don't know, maybe there's less if people more educated are worried about their weight or something, or their fat intake. I don't know. But this is a classic definition of something that is not, it's still relevant in randomized, where's randomized? Randomized trials, but less relevant. Because if you randomized everybody to chocolate, you would, through randomization, make everything equal on income and education, and you would basically be making, you would basically be making all these links disappear. But we're going to put these links back because we haven't randomized, and we're not able to do that. So this is something called, that does happen in non-randomized trials, called a confounder. And you need to identify these in your DAG. These are very important for ascertaining causality. And so what this means is, if we know this income is positively related to chocolate and positively related to Nobel Prizes, you can very simply see if this is a positive association and this is a positive association, by definition, even if there was no real connection between chocolate and Nobel Prizes, just because of this alone, we could see a false positive correlation between chocolate and Nobel Prizes. So this is kind of like the enemy, or the bad, kind of the toxin or pollution that can come into the analyses that vast majority of you are going to be doing, is these confounders. And you need in your design a strategy to deal with confounders. So I'm coming back to design, okay? This is where design, critical in your design, we need a strategy to deal with these confounders of the relationship. Now, what are those designs? Now we're going to start moving. Now is the time we can start moving into the how. Okay, we're going to get there in just a second. We need a strategy to deal with the confounders. I can't overstate how important for the vast majority of you that is going to be. Now, what can you do? Well, one thing that our team spends a lot of time on are doing things called natural experiments. And these look for kind of randomization that happens in the real world by, in a way, accident or through policies or other things. So we're trying to simulate a randomized control trial. What could that be? What could that be? Things like maybe there's a trade deal that between the US and the Pacific Islands, and that trade deal suddenly makes the cost of chocolate much lower. And so suddenly we see chocolate shoots way up. Now the trade, right? You can think things like this that are outside the control of individuals that can lead to big changes, and they act in a way as if it were a randomized control trial. I don't want to get too much into that, but one way in your design, this is more advanced, is to try to simulate a randomized control trial in real life. That's one way. Another way is through matching. So this is also common. Maybe you try to say, let's take two, right? So we're going to try to simulate a trial again. We're going to try to take, okay, let's take two countries that have similar income levels, right? And then, but they have different chocolate, and see if they differ in their Nobel Prize winners, right? So instead, we're going to try to, we know that this is here. We're going to try to get rid of this confounder. I'm going to take education off the table just to kind of make this easier. So we're going to try to do this. We're basically going to try to wipe this off the table by holding it constant. Randomization was our tool to hold it constant before. We're going to try that instead through matching. That's one possibility as well. Okay? That's a design strategy, but you got to deal with these confounders, because otherwise you're risking a false relationship. And many papers have published these false relationships. You got to be careful with them. And I say many papers, I'm just going to come back for a second and show you what I'm talking about. Because, right, it's not like this is a thing. Let's chocolate Nobel laureates. Here we go, right? Here, where is it? Chocolate. Here we go. I mean, I'm not kidding. This got published in the New England. Could there be a correlation between a country's chocolate consumption and total Nobel laureates. Okay, I don't have a full article. If you guys want to read this, check it out. It's pretty amusing. Okay, so this stuff actually does happen. People publish research that I think is completely spurious and confounded. And here's an example of it. I think they might have done this for humor, but still. Okay, I digress. Let me come back and share the whiteboard again with us. So that's what I'm saying. It's really critical that you guys define this. Okay, so matching is another tool, right? And what's this going to do? It's just going to try to hold constant. Then what's the other technique? Now we get into these are you're working through design. These are design solving it, and now we can use statistical tools to try to solve it. And one of those statistical tools here that many of you talk about, and it's a really common entry point, is multivariate regression. And in the regression, you're going to try to hold constant through a regression model. And I'm going to explain how that can work. I hope this matching idea makes sense to you, because it's gonna kind of help you to understand a little bit about what's going on. So this is a quite good one. There are other techniques that, again, advanced techniques like instrumental variables that get into more advanced econometrics and epidemiology that I don't want to get into. That's for a later day. But the vast majority of you that I've seen in my experience working with students, will kind of gravitate here. And that's often because maybe that's what your supervisors are recommending, that's what you've heard about, that's what you think is important. So next I'm going to start moving over to multivariate regression. But what you need to have clarity on, coming back, in your design, you need to have a design and you need to draw a DAG, where is this DAG, in which you identify the primary potential confounders. You need to already have a good idea about this, and this is going to be important as you come later to writing up your results section. Because what happens so commonly, you submit a paper for review, and the reviewers are like, I don't believe this chocolate Nobel Prize because it's just confounded by income. You haven't dealt with the potential confounders, and then smack, reject. But you're going to be, right, you've learned from me, you're not going to make those rookie errors. You're going to say, actually, hey, we thought about this. We knew income was a potential threat to our ability to identify a relationship between chocolate and Nobel Prizes. So we actually dealt with this. We are one step ahead of you, evil reviewer number 2. We already thought about this, and this is how we anticipated it. This is how we dealt with it. And this is how we know income is not creating a spurious relationship, which we are reporting. Okay? So you need to do this. And right, this is a fundamental step, because many people say, oh, I want to do a multivariate regression, but I don't know what to put in the model. Well, you need to draw a DAG. What you put in your model is going to shape what you are trying to, is going to affect what you're trying to show, what relationships you're trying to articulate, and what things that you think are potential confounders that you want to try to hold constant in the way that we could try to hold constant with matching or knock out with randomization. Okay, one other thing, I need to expand our thinking on DAGs a little bit and share with you one other thing. So, right, sometimes I see people then saying, okay, chocolate causes Nobel Prizes, but it's not direct. It's that what happens is if you eat chocolate, you're going to be more intelligent. And because you're more intelligent, because chocolate's making the whole population more intelligent, then you're going to be more likely to win Nobel Prizes. So what have they done here? They have articulated, right, a mechanism. So this mechanism is very important to understand. This mechanism is very important to help you, can also help you. Because what you might want to do is already think, well, maybe if I can prove the link that chocolate causes you to be more intelligent, and if I can prove the link that if you're more intelligent, there's more Nobel Prizes, well, I've kind of indirectly proven. I've proven this part of the causal chain. I've proven this part of the causal chain. It naturally follows that if this link is causal here between chocolate intelligence and intelligence Nobel Prizes, I have now convinced you that chocolate causes Nobel Prizes. So that's another way to go. And this is a way, sometimes when you do quantitative work, right, you're kind of putting together bits and pieces. And I like to think of it as you are like a lawyer building a case for a causal relationship. You're building a case. You're building evidence, saying, no, this income didn't confound it. It's causal for this, this, and this. And we'll come back to a little bit more talking on causality. Okay. So this is a mechanism. Now, what happens, I see so often happen, is people say, okay, I'm going to look for the relationship of chocolate with Nobel Prizes, and I'm going to hold constant income. Great. I'm going to hold constant income. If I hold constant income, well, if you hold something constant, then you kind of taking it out of the equation, then income is no longer shaping Nobel Prizes. But suppose now you hold constant intelligence and you block this pathway. Well, and then they find, oh yeah, chocolate no longer causes, and chocolate's not a real cause of a Nobel Prize. I was like, well, yeah, but you just you held constant its pathway, its mechanism. You blocked how it works. Of course, you're not going to see that it has an effect anymore because you blocked it. So this is very important. So again, coming back, when people say, I don't know what to put in my model, well, you don't put the mechanism directly in your model because you're blocking, right? Chocolate's causality flows here. You're blocking that flow. So that's why it's also important in your DAG to identify confounders. And you may also want to think about identifying these mechanisms because they can also help you along the way. They can help you maybe build your case for causality. And they can also make sure you don't make mistakes that actually wipe out what you're trying to study in the first place. Okay, so we've already covered a lot of ground here in a short period of time. And where are we still? We're still on the left side of the what. I guarantee you, if you don't have clarity on your confounders, your mechanisms, and the design, you are in for a world of frustration and headache. So if this is you right now, and you are sitting on Stata or SPSS or R trying to run regression models, and you're feeling confused about what's in and out of the model, you need to take a step back. You need to take a step back and get these things lined up. Let's move over to how. Now, how is in this land, like I talked about, of multivariate regression. That is kind of a workhorse. I saw somebody posting the other day on Twitter that whoever invented multivariate regression should win a Nobel Prize. I mean, it is really bread and butter. Why is it so bread and butter? And I'm going to talk about this in a second. And how does this help us map out a causal chain like this? Remember, we're in this non-randomized world, we're going to have confounders. All of your studies in a non-randomized world are going to have confounders. I'm going to repeat this again. All studies in a non-randomized world will have potential confounders that you will have to deal with and you will have to discuss. All of you need to identify confounders, all of you. So think hard about what they could be. Okay, so multivariate regression is powerful. It's a workhorse. It is bread and butter. In my quantitative papers that I published, over 200 papers in quantitative work, I would say almost all of them have employed some kind of multivariate regression in them. Even if I did other designs, natural experiment or matching, still, or difference in difference is still in a multivariate regression framework. So, I'm not saying you have to do this, but it's very common. Let's talk for a second first, though, about what regression is, and then we will progress to the multivariate case. Okay, regression. For some reason, people get really scared when we talk about regression. And I think it's just taught in ways that are much more complex than needs to be taught. Regression's not that complicated. I even think that somebody who's 5 or 6 years old can understand regression. Stay with me. I'm not trying to offend anybody, but I really think it's simple. If I gave this to one of your children or something, said, okay, here's a whole bunch of dots. Okay, can you draw a line for me that cuts right between those dots? And I'm pretty sure that a 5 or 6-year-old could do that. They say, okay, they probably draw a line like this. Okay, you've got some creative 5 or 6-year-olds who are going to be like, ha ha ha, I'm not going to do it. My parents told me I'm going to do that. Fair enough. Okay, but they could do something like this. Okay, the line might go a little bit like this, it might go a little bit like that, but it's going to end up looking something like that. And there's somehow naturally you can kind of just see, yeah, I could do that. This is where I want to say, let's look like the car. Let's lift the hood and look at the engine of what we have actually done by drawing this straight line. Right? So what we've done is intentionally by drawing this line that cuts through the dots. Look at the space between the dot here. I'm going to zoom in to see this a little bit better. Look at the space that's here. Let me use a different color. Look at the space between the dot and the line we drew. See the space? These spaces? Okay. What we have essentially done, imagine we've kind of pinched the space. We've tried to make the space as small as possible. And in multivariate regression, right? Or in regression generally, right? We are trying to minimize the distance between these data points and the line. That's it. We're trying to minimize this distance. Okay. Now, you guys know that this could be our chocolate. Oh, sorry, this would be Nobel Prize. But again, Nobel Prize. And this would be our chocolate here. So we have all these observations on how much chocolate's eaten over here. We have the number of Nobel Prize winners up here. And we are connecting a line to try to fit this. And we have different components then that happen. But really, that's all that's going on. That is all that's going on in regression models. So sometimes regressions are talking about, if you hear this taught in classes, they're minimizing the sum of the least squares. And sometimes you see people talk about OLS, ordinary least squares. Well, what is this whole thing about squares going on? Well, just think about this. If you look at the distance between the line here, the line and the dot, you could say, well, this is plus, I don't know, this is maybe, let's say 5. It's off of the line by 5 Nobel Prize winners, is off of the line by -3. And let's say we add up all these distances, right? So you could say, if I wanted to find the best line, let's say I draw a line here, well, the overall, if I added up all these distances, this rainbow line I drew here is more distant, and you would just see it's off. The problem with the sums is if I start adding +5 and -3, well, then I get 2. Well, that's not right. So to fix that problem and make everything positive, they take the square. That's why they're called squares, right? Because you're not going to add up positive and negative. You're just going to add up to 0. That's not helpful. So instead of taking 5, you take the square of that distance. You take 25 and -3. You end up squaring 3, and you get 9, right? 5 times 5 is 25, and 3 times 3 is 9. And you sum those numbers up. It's just essentially done these squares to make it positive. So there's no magic there. There's other ways you can do this. This is not the only way you could set up a regression model to optimize things. You could do the absolute value. You could even, there are ways you could do the regression model, right? We're looking at the distance from y. There are models that actually take the distance and they say, take this distance here. Like minimize these distances. I'm not going to get into variance, right? The most standard one is the one that I'm sharing with you that uses squares to solve this problem and uses a distance based on vertically here rather than horizontally. That's just kind of convention in the field. Not necessarily right, wrong, superior. It's just what's used. Okay, and that's why sounds so fancy. Yeah, I'm gonna use ordinary least squares. We're gonna minimize the sum of the least squares. Sounds so complicated. Hope you guys can see it's something that a 5 or 6-year-old intuitively understands. And that's my problem, like I said before, with a lot of the statistics training. Intuitively, people get the intuition first. So I hate that people teach, let's go with this complicated stuff. Let's give you a complicated math equation that's going to be like the sum. It's going to end up looking like the sum, right? Which many of you guys freak out when you see that. Of the least squares residual. So the residual is going to be the y hat minus the whatever the line is, the y. And we're going to have this be squared. And then we're going to put a minimization function on this. Right. And you see something like this and you're just like, what? Right. And it's just completely unnecessary. Don't start by training with stuff like this. But now that I've explained to you the intuition, you can understand what's going on with that kind of equation. You guys are, vast majority of you are not going to need that. So I just want you to understand the intuition. Okay. So what is that doing? Right? It goes back to our conversation a moment ago of saying this is going to describe this correlation. This is describing the correlation here, right? And so often we say, right, when it's moving positive, right, that's a positive correlation. And this would be an example of a positive correlation. Chocolate goes up, Nobel Prize winners go. Okay, hope you all have got that so far. Now I want to move us to the multivariate case. Because what we're doing in a model is essentially we're going to say Nobel Prizes are a function of some constant plus this line, which will be x and chocolate. The slope of the line is this line that we have calculated, right? It's what we've drawn, right? I hope you guys know the basic algebra of slope of a line, but it's just kind of, it's a straight line. So you can see, right, it's kind of like the angle at which it's going. And the constant is going to be when chocolate is 0, how many Nobel Prizes are there? And right, when we don't know what that is. It's the base rate of Nobel Prizes. Nobody, your model would be saying your constant is nobody eats any chocolate, right? Chocolate is 0. What is the point right there? That's your constant. So your model, when you look at multivariate regression, is telling you these two things. This is kind of like how steep is this relationship between chocolate? The higher this number is, kind of the steeper the line, right? A higher number here, that would be a steep line. This would be a not so steep line. That's what that's telling you. And then in this model here, you have an error term. Error term is very important. This error term were these lines, these distances here that we talked about. And I hope that makes sense. This error term. I hope that makes sense. That's all the error term is. So if you add these things up, right, the constant, well, you can find any data point. If I want to find this data point here, right, this data point here, where the little hand is, right, it's constant, plus chocolate times whatever this thing was. That'll put us right on the line, plus this error. And that'll bring us right to the data point. Any questions? We've gone under the hood on regression in the single variable case, right? So if you want to interpret this stuff, right, you already know how to interpret, right? If you're writing up your results, you can say, right, the base level, the model estimates that when, right, there's in a world where there's 0 chocolate consumption, there would be this many Nobel Prize winners here. And for each kilogram increased in population chocolate, we estimate this many more Nobel Prize winners. That's you just describing whatever you've estimated the slope of the line is. And you want to keep that interpretation really simple. Okay. Now, to me, this is something that I had to dig up and I wasn't taught, but initially, it began to make a lot of sense later on. So here's what happens. Let's say we take income, okay, instead of chocolate. And this is the line. What is going on with multivariate regression? Now we want to take chocolate and we want to add income. And we want to say, okay, here, we want to also estimate a line and a slope of a line with income. Okay. So what happens? Think of this as multivariate regression doing the same process that you've seen, but multiple times. It's going to do the same thing for multiple variables. Whoa, okay, but how? Check it out. This is what it does. So it first looks at, let's say, the relationship between Nobel Prizes and income. And what do we have left? We have left this distance from the line. We have this distance from the line right here. Now what happens? Okay, we take this distance from the line, and now we have something new. Now we have something else. We're going to have something Nobel Prize after, let's see if I can find that. Oh, shoot. I'm looking for a certain key on my keyboard, and I can't find it. Hang on, guys. It's a kind of straight line. Oh, shoot. I'm not going to be able to find this. You know, this is the problem. I have this Italian keyboard, and okay, this is not the right note. I'll do it like this. It's a Nobel Prize. I'll draw it with this thing. Nobel Prize net of income. Why? Because we have now taken whatever income can explain. We've already kind of parsed that off. We filtered that out. Oops, that's the error. So what's happening? So now we have these data points. It's like you got a new data set where you took income out of the equation. Income got taken out. So you've got whatever Nobel Prizes that income could not explain, could not account for. What can explain that? Can chocolate explain what's left over after that? We've already explained what Nobel Prizes can be accounted for with income. Can chocolate explain anything over and above what income could explain? That's what's going on. So your new data points, your Y is not Nobel Prizes anymore, but it's actually, if you look under the hood, what's going on is these distances from the line. The distances from the line, which is a little bit hard to draw because I need to draw the next thing. So this is also complicated. What's going on this X? Well, you're not looking just at chocolate specifically. You are looking at the chocolate that is not explained by income. So behind the scenes, the sleight of hand, there's not just 2 regressions going on, but there was another one. There's another regression happening. Whoops. Let's see if I can take this. So what's going on? There's actually a regression here. Oh, we'll add this piece too. Oh, no, I can't seem to add. All right, I'm just going to draw it. There's actually another regression that happened. Chocolate. Whoops. On income. looking at why are we doing a relationship? Wait, what I'm doing a multiple, what am I looking at that for? Because we're actually calculating this relationship. So, right, to deal with our confounder, what did we have to do? We had to do income in the Nobel Prize, but we also have to look at chocolate and income. So chocolate and income, what's going to happen? Well, say there's a whole bunch of dots here. Again, and income has a positive relationship with chocolate. Now your new variable for chocolate is going to be the chocolate that is unexplained by income. Chocolate unexplained by income. So you're going to get a new variable. That's what, once again, distances from the line, right? That's the chocolate that income can account for. All right, if this was a perfect line and the line fit everything, it's like, well, they're perfectly correlated. Income and chocolate, they're basically the same thing, right? But that's almost never the case. You'd never have that perfect correlation. So that's what's going to go on. This chocolate, you're going to have the chocolate that's unexplained by income. You have this new model coming, right? The chocolate unexplained by income, the Nobel Prize unexplained by income. Then you're going to look at that correlation. And how's that going to look? Well, okay, I'll try to do an example. So you have a data point here, right? So you have a distance here of this for chocolate. So that's going to be, I don't know, on that distance there, let's say that's there. It's going to be about right there on the graph. And what's the data distance here is about there on the graph. So the data point, right? This would take a while to do, right? The data point would be about there. What's that data point coming from? This distance here is going to be moved here because that's the chocolate variable. And this distance here on the Nobel Prize, this distance here is going to be the Nobel Prize, the error that was the thing that income couldn't explain is going to be up here. And so the data point would be about there. Okay, it is getting, you can see multivariate starts to get more complicated, but this is how, this all comes back to how multivariate regression is trying to deal with this confounder issue. It is trying to hold constant this and hold constant this. Why? By taking what was unexplained of chocolate from income and what was unexplained about Nobel Prizes of income. So you have, through this multivariate regression, you have blocked a potential confounder. This blocking is not always perfect. It's not always perfect. That can happen for many reasons. Why could this blocking be imperfect? Well, what if you got the relationship wrong between, say, income and Nobel Prizes, right? For example. And this is where, to see if this is working the way you want it to, we get into a world of diagnostics. And I don't want to go too far in these diagnostics, but I'm going to give you a few because we can do a whole lecture on diagnostics. Right? Your diagnostics are all about, is your model working well? Now, in a world where, for example, if your data look like this, let's say the data points are like this, well, you could see, well, maybe, let's do something like this. Let me do another example. I'm going to zoom in so you see this. Let's say your data look like this. And basically, in a world, you say, okay, at low income, there's a lot of Nobel Prize winners. Maybe the people are deprived, so they really try to innovate. And then they get middle income, they're really comfortable, they don't want to do anything, and then they're really rich, and then they have the resources and they're brilliant again. Okay, if you ask a 5-year-old to draw the fit of this line, it's much harder. Right? Our tool is a straight line, but you can see the real relationship here looks like a curve. Well, in this case, you're going to have a bad looking fit. And how can you see that? If you do a regression diagnostic, you take that error, and sometimes this error is sometimes called a residual. You take this gap, and if you plot these gaps here and say, okay, let's just make a new variable like we were doing before, and let's just make this error and plot this error against our line, our prediction. What are we going to get? You're actually going to see something that does not look like it should. Okay, your error and your prediction line, you can see this error right here. It is going to look, it's going to look a bit funky. You're going to see a pattern happening to this error. It's going to look a little bit like, I mean, I haven't plotted this out, but basically at the early stages, you're going to have a lot of error. It'll be up high error, and then you're going to suddenly go to, right, you're going to have lower errors, and then they're going to get really high error again, and then it's going to go back down, and then high error again, right? I hope you can see this. There's not so much error here when you get close to the line at these 2 points, but then there's a lot. At any rate, I might not have done this perfectly, but the point is you're going to see a pattern if you look at your errors. If you see a pattern, it's a sign you haven't done a good job dealing with this confounder. You haven't done a good job dealing with this confounder. What happens? You haven't blocked this pathway. You haven't done a good job blocking, and you could get a false relationship between chocolate and a Nobel Prize. That's why we're doing these regression diagnostics. So what does a healthy line look like? Remember what I talked about before? We are trying to achieve randomization. Why? Because randomization is like that secret sauce that makes all our pain and problems go away. We want it to look random. We want it to just be like this, no pattern. This is a healthy line. Healthy line like this is what you see here in our, where are we? Here. This is these just look random. No clear pattern to being off. So that's the most basic, this is the most basic diagnostic you can do. Okay. The other thing that this basic diagnostic is going to tell us is if maybe everything looks random here, but then you got a point that's like way out here. That is sometimes called an outlier. Why is it an outlier? Because it's lying out. It's really far afield. Outliers are interesting. Some people want to throw them away. I like to probe them deeper because there's sometimes exceptions, and these exceptions are fascinating. You can learn a lot from these exceptions. So sometimes you may, even in your results, figure out there's an outlier. Why? Sometimes that why might tweak you to revise your model. Maybe you missed a confounder. You might need to go back and revise your DAG. Maybe there's a story. Sometimes there's a story. How did this country, for example, imagine our chocolate Nobel Prize looks like this. Chocolate Nobel Prize, or sorry, I changed it to income, but okay, let's put it back to chocolate for a second. Let's say it looks like this. Everybody's following this curve, except up here we have, I don't know, let's say we have Kuwait up here. How did Kuwait, well, Kuwait's actually more rich, or maybe doesn't eat. They don't eat a lot of chocolate, but they got a bunch of Nobel Prizes. But there's a story there, and that's really, that's a fascinating story you want to probe more deeply to try to understand what's going on. You may want to write up about this. Cool. I'm intentionally not using the jargon, because think about it at the beginning. If I just went and said, Abo, here, you need to go, let's go to the how, and this is what people will say. How, okay, in the how, you need to do a multivariate regression, and you need to do as a diagnostic, a residual versus fitted plot. This is where a lot of people approaching it for such time are like, oh, this is, so frustrating. I want you guys to understand why and how you're doing these things. What is the whole purpose of this? Because when you understand why, it's going to stick, and you're more likely going to use it in the right way. So sometimes, right, this tells you need to do something. It could be you need to say, okay, this graph that I had here of income following this pattern, I need to do a transformation to make this this variable, this income, sorry. Say maybe you're going to look at the distribution of your income data, and you find the income data is skewed. So there's a lot of people with low income and then a few with high income. Maybe you need to do something to make it look more normal to deal with skew in the data. There are different things that you can do. This is going to get a little bit beyond, but you want to look at your data. Your ideal data will kind of follow a normal distribution. And normal distribution is simply kind of this what I was drawing. Kind of follows, if you look at your data, and that's a terrible graph, it follows this kind of curve. This kind of curve is this is kind of if you look at income, I don't know, I'm just using now chocolate, let's say chocolate consumption, right? Some people, right in the middle, there's an average amount. Some people eat a lot, some people eat a little, right? And this is kind of this is the proportion or the percentage here, right? And this is kind of like the median consumption. I don't want to get too much into those transformations. What I want in this first session that we've done together is I want you to understand, I want you guys to all go through this and go back to your work. Figure out what the gap is, figure out what the research question is. We got a dedicated training on the gap. If you don't know what the gap is, the research question should follow from the gap, and your design should follow from the research question. In your design, you need to figure out this DAG, and you need to think hard about confounders and mechanisms. All of you should have a DAG in your quantitative analysis. I repeat, all of you should have a DAG in your quantitative analysis. And you need to think about what level of analysis that's going to come from your data, and if you're going to look over time or not. A lot of these things, guys, we're compressing a lot of information in a short period of time. Right? We could do a whole session on overtime. We could do a whole session on building a case for a causal relationship. We're not going to be able to do that in this short time. but I want to get you some things that you can already use now. And I wanted you guys to understand that the confounder is the most important kind of evil sin, like that's messing up your model. And I wanted you guys to understand how regression looks for a relationship between the two things. And then when you start going in the multivariate setting, we've looked under the hood to figure out how you can better pinpoint these relationships. Just in closing, when you write up your results, because I want to say something for Jay on interpretation, I always make something called a result set. And that result set usually consists of descriptive statistics. It usually consists of the DAG, and then it consists of tables and figures that speak to my research question, that test my research question. It could be a table of output from a regression model that tells me what are all my coefficients, where are my coefficients, I'm making everybody dizzy here, these coefficients here in my model. It might include even some residual plots. I sometimes put those in the appendix to show everybody my model's pretty good so they can trust me. It might show figures that show some specific outliers that I want to pick back up and talk about in the discussion. It might show some figures that show that my confounders are not really a problem and convince my reader and reviewer that I've dealt with them. But I always encourage you before writing, right? Like I said, you need to know your research question, clarity on why you chose your design, justify your design. That's all going to be in your methods, and create this result set. Tell the story here. Once you've got that story in your tables and figures, then you can move to writing up the results section. If you don't have that clarity from your tables and figures, if you don't have that clarity on how your model is set up and conceptually what's going on, you're going to have problems, and they're going to manifest in your writing of you feeling stuck. And that writing is not a problem of you being inadequate, incapable. It's just you're trying to do the impossible because you haven't taken the right steps along the way to get to that. We've covered a lot. I think this is a good stopping point for today. Stay tuned for more on that. Really, really excited. We'll do this as an installment. I've developed this in the background as a step-by-step course, but in the spirit of open access, I want to make this available to the whole world and accessible to you. And that's really what Fast Track is all about. I really want to democratize this knowledge that I learned myself when I was a PhD student in training at Cambridge and did my master's at Yale, and then passed on to my students at Ivy League universities. I want to transfer this knowledge to you with the hope that you too will one day transfer this knowledge on to your students and peers and colleagues, because that principle of sharing is really, really intimately linked to the mission of Fast Track. All right, guys, have a great day, and I'll see all of you in the DMs. Bye for now.